Hi, in this session of Surely Physics, we're going to look at writing a free-fall lab conclusion. The prompt is given here at the top. We're mainly looking for what affects the acceleration of falling objects on Earth. We're going to follow it up with the second question: is there a limit to the rate of acceleration of a falling object? As you approach a question like this, you've done writing like this before. It's argumentative writing. This is something you may do in a language arts class or a history class, social studies. You're trying to make a point, you're trying to argue that point, and follow it up, back it up with information. That's all you do in lab conclusion writing. The conclusion is going to be scored on 3 rubric points: use of information, supporting details, and terminology. For use of information, basically, are you responding to the question in full and completely? So is the response to the problem complete? Are you responding to the entire thing? Have you addressed all the components? So in this question, there are really 3 components. What effects or what factors affect the acceleration rate of a falling object? We investigated 2 factors, so you should include a discussion about those 2 factors. And the third thing would be, is there a limit to the rate of acceleration? So in this case, does there seem to be a maximum to your data? Does it seem to plateau? Do you think dropping a rock or a car or a building off of a cliff would have any different acceleration than what your maximum acceleration rate for your dropped objects was? So that's what you're responding to. There's 3 things. What are 2 factors, and is there a limit? So that all goes into the use of information, as well as factually accurate. So are you using the facts in front of you accurately? The second rubric category is supporting details. Is data cited to support the concluding statements? So if you don't support your statements with any data, then you get a 0 for this entire section here. 2/3 or 1/3 of it is a 0. So definitely you want to support it with data, not just vaguely refer to your data. You've got cold hard facts in front of you. You've got numbers. Use them. Use them to support your statements. Do you identify also? This is going to be like a follow-up piece. Are you identifying strengths and weaknesses of your experimental design? So in the end, if you find that you've got some pretty strange looking data, or it doesn't agree with what you really observe or you understand about free fall, you may look into your experimental design. Is your data starting to show a trend, and then one data set is just like way off, it doesn't really agree with the rest? And sometimes that happens. So it's good to reflect in that case and explain any strengths and weaknesses of your experimental design that might account for those difficulties, those problems in your data. And are there ways to improve your experimental design? So if you just like totally got way off, like your data is crazy, and you probably have had that before in a science class, like I have no idea what's going on here, I thought we were supposed to get this, but we actually got this. Does that mean you're going to fail the lab conclusion? No. Why don't you go in and think about ways to improve the experimental design? What are some weaknesses? That's what you can approach instead of explaining the question for which you have data that doesn't support anything. You can go in and look at your data. What does your data support in leading you to design an experiment the next time? Because that does happen in real life science data collection. Finally, the third category, just throughout your writing, use your scientific terminology, the terms that are new to the unit. In this one you might have displacement, velocity, acceleration. Are you using those correctly in the right context? So does vocabulary show scientific understanding? And also, are your units and labels accurately used? Every measurement you have, every number should have a label to it, a unit. And are you applying that correctly? So in these couple of examples or samples here, these are samples from my previous classes, actually several years ago. For their lab procedure, they were dropping objects off the back of these bleachers, like in the sport stadium. So they had, good 20 feet or so to drop these objects, and they were using stopwatches. And these were their conclusions. So I'd like to go over some strengths and weaknesses of just a couple of these to give you guys some good ideas on how these are scored. Our first conclusion here: According to our data, our hypothesis was incorrect. First off, you don't need to talk about hypotheses at all. Let's get to the point. Let's answer this question. What affects the acceleration of a falling object? Let's identify the thing first. What are we going to identify as an effect of acceleration? Is mass or surface area / size, are those going to be a factor? Let's get right into it instead of giving a big introductory sentence. We said that weight would not affect the acceleration of a falling object. Okay, I can see where they're going here. In our experiments, the average speed of the non-weighted tennis ball was 1.19 seconds for an average acceleration of 7.77 meters per second. So I see some strengths here. They're labeling. Here's an acceleration and a number, and it follows up with a unit. You can also use meters per second squared, but meters per second is okay. So this is an example of good use of that last terminology piece. A value is given. They identified it properly with acceleration, so that's good vocab. The units are accurately used, 7.77 meters per second. However, earlier in the sentence, there's a little problem. They say, in our experiments, the average speed of the non-weighted tennis ball was 1.19 seconds. Do you notice a disconnect there? First off, they didn't measure speed. They measured distances and times. And they provided a time here, but not a speed. Second, this value is not a speed, and it's not really relevant. What we really need to look at here is, go back to the question, what affects the acceleration of a falling object? So they can just focus on, they could forget this whole average speed thing. They could just say, in our experiment, the acceleration of a non-weighted tennis ball was 7.77 meters per second squared. It would be directly more to the point. Moving on. While the weighted tennis ball had an average speed, again they have a problem here, of 1.13 seconds, the acceleration 8.61. They should include that meters per second squared there and get rid of the speed and the 1.13 seconds. So here they've compared the non-weighted tennis ball to the weighted, and we can see that the weighted has a greater acceleration. They go on a little bit more, and this might be too much information. The weighted tennis ball, it'll obviously have more weight, so I don't know if they needed to go here, but it's okay that they included this. The weighted tennis ball weighed 91.7 grams more than the other and had 0.81 more acceleration. Okay, they compared it. But then look what happens next. The paper box full of paper clips. They just went on to something different. What are they trying to say with this comparison? Make a statement. We found that weight affects acceleration. The heavier objects tend to have a greater rate of acceleration. For example, the weighted tennis ball had an acceleration of 8.61, which was 0.81 meters per second squared greater than the non-weighted tennis ball that had an average acceleration of 7.7 meters per second squared. See, that you need to make a statement here, make a bold statement, and back it up with data. All right, that would make this a lot stronger of a conclusion here. Now they're moving on. Paper box full of clips, and the paper box not full of clips. The unweighted box had a different acceleration rate. They just start listing data here. So this is kind of data overload. Please do not rewrite your data table in a paragraph. Make a statement, support it with the relevant data, and move on. Okay, people can refer back to your data table. You can even say, and this trend followed as I added more weight to the ball, or in our lab, we added more weight to the box. Those are good words to use, and you can move on with your paragraph. Now, as we move on, and if you read through this, it doesn't really address surface area. They just keep listing data, and it just kind of ends there. So this conclusion is not responding completely to the question. They didn't talk about a limit to the rate of acceleration. They're not talking about surface area. So it is incomplete. There are some factually accurate statements, but very poor use of data. So I'd probably score this a 1 or a 2 for use of information. For supporting details, they are citing details. They don't give any strengths or weaknesses to experimental design. They don't talk about that at all. So you do definitely want to do that. The reason for doing this is validating your data. What happens at the end of a paper that you're writing in social studies? You probably make claims and support it with statements from people or primary sources. But what do you have to put at the end of your paper? A bibliography or a work cited, cited sources. Different classes call it different things, but basically it's where'd you get your stuff from? Are these relevant? Are they valid sources of information? Or did you just ask your Uncle Eddie what he thought about the subject and use that as factual, proof? Uncle Eddie, if he's a college professor, maybe that's good. It's valid. But if he's not an expert on a subject, you can't really use that as valid support. So talking about the strengths and weaknesses of experimental design validates your data. Your data supports your arguments, and that makes your argument strong. That's how it works. All right, I'm going to move on. Let's look a few things in this next one. Problem in our experiment was to see how long it took. Okay, they introduced it here. You don't really have to do that. You can get right to the answering the question. We used many different objects. We weighed it. Some of the objects we dropped were this. Our hypothesis was the size and mass of an object. In fact, we thought that the objects they're giving a recitation of event, step by step. We don't need to recite the procedures either. Let's get right to the argument. Here we go. The less surface area, the more mass led to a quicker acceleration, which made it hit the ground faster. Start there. Then go with your data support. Okay? I can probably axe this whole first part of the paragraph and get started right here. We found that lesser surface area and more mass led to quicker acceleration. Then go into the proof. Moving on. Conclusion 3. Now this one is lengthier, but I think it's got some good stuff. Again, you don't need to start with the hypothesis. We hypothesized that the weight and shape would affect the acceleration. That's great place to start. For example, the ping pong ball and foam ball are exactly the same size. They weigh differently. Blah, blah, blah. They started listing stuff that's directly on their table. They could just refer to it instead of rewriting it. All right, the ping pong ball weighed this much and had acceleration of this much. Well, the foam ball weighed a little bit more and had acceleration of less. This shows that the material on the greater weight also has a greater acceleration rate. You notice the weakness? I think they mixed up their data a little bit, maybe swap these two numbers. So they had the correct conclusion that a slightly greater rate also had a slightly greater rate of acceleration. But if you notice, their data that they cited doesn't agree with that. So make sure you're citing the correct data. Look over it when you're done. I think that's a weakness here. All right, in this one, read through this one if you will. You can pause this if you want to. They start talking about sources of possible error. This may help you as you're writing yours. It's a good sample to think about that weaknesses of experimental design, how to improve it. Finally, conclusion 4. This one's got a little too much flair, but it has some good stuff to it. Shape and mass do affect acceleration, right to the point. For instance, a rock which weighed this had a chunky shape and the fastest acceleration of this. Now this number is a bit high for the actual value that they probably recorded. Whereas the flat cloth filter, which had a much lesser mass, showed that it did affect acceleration. The rock weighs 16 times as much. It's a good comparison statement. And the crumpled filter had a greater acceleration. They're pointing out some very good pieces of information here, but they're not making a very good bold statement. So make sure you make those statements. This is how weight affects it. This is how surface area affects acceleration. Here's my proof. Here's some sources of error. And also, getting back to 3, I forgot about this one. They did have a discussion about a limit, a possible limit to acceleration. So I'd say conclusion 3 is the most complete. Their response to the problem is complete. They addressed all the conclusions components. Now there was some factual problems way up here, just one little piece. So I might drop it down for that. So use of information, this one gets a 3 or 4. Supporting details, did a pretty good job, probably 3 or 4. I didn't read through real well this time. And terminology was pretty good. So overall, this one would on a whole probably get a 10 to a 12 out of 12 points. So I hope that gives you a good idea of how to write these and some ways to bring strength to your writing. It doesn't have to be long, but it has to be complete. Make sure you get to your 2 facts, mass and size, how those factors affect acceleration and rates of acceleration. Give strengths and weaknesses to your procedures, and don't forget that data support. Keep it concise. If you don't want to refer to all your data, you can point out a good piece of data and refer to the rest, and this trend continues in the rest of our data. Those are good words to use. I hope you get some good practice with that. Bye-bye.